D.4, hints for final, part 1, question from 1 through 4. All right. The first question, in order to find the median of a given array, is it a good idea to sort the array first? The question is, if you do the sorting first, what is the cost? Okay, so what is the cost? Sorting. Okay, yeah. For the worst case, the cost. You can use any sorting algorithm, but if you do that, you need to pay this much. Okay, you need to pay this much. But to find the median, can you do better than this? Better than n log n? Is there an algorithm that can find the median better than big theta of n log n? Median, we know it is a special case of the selection problem. Selection problem, right? We have one part we talk about how to solve selection problem. We spend a lot of time with, find the general solution, selection problem. Median is included. Median is a special case of selection problem. So if we can solve any selection problem, definitely we can solve the median problem, right? Yeah. Can we do better than this one? Yeah. You can find the answer in our notes. Yeah. In our notes, you can find it, the answer. Yeah. All right. So number 2, given a heap, if we know that the number of leaves is greater than the number of internal nodes, then we can say this heap has odd number of nodes. Greater than. Leaf is greater than. Here, if you look at the, all the possible cases for a heap, there are two cases. One case that corresponds to full binary tree. One case. Okay. So the other one is number of leaves equals number of internal plus 1. That's one case. Another case, not a full binary tree. Yeah, not a full binary tree. Okay. In that case, number of leaves equals number of internal nodes. Okay. No plus 1. The difference is that plus 1. Okay. Now, because greater, that's the first case. So now in the first case, okay, all right, yeah, you need to determine if this heap has odd number of nodes. All right, so that's question number 2. Number 3, average case. Insert an element into an ordered array with 25 elements. How many comparisons do we need for the average case? Assumption, we use the linear type search type insertion, do comparison from last through first. The standard insertion step. Okay, yeah. Here, I want to use this similar question in comprehension question module 4, part A, question number 4. Yeah. in that one, this is the answer. Here, I just want to explain this answer. Then, because here the only difference is 30 and 25. That's the only difference. Okay, yeah. All right, so let me explain this 30 case. Yeah. All right, so the element position, let us use number 1, 2, 3. Okay, all right. The last one, 29, 30. All right. Okay. When you do insertion, given a key, yeah, the possible cases, you have 31 slots. So look at that. So 1, 2, 3, right? Yeah. All the slots separated by these 30 elements, 31 different cases. 31. So that's why our denominator is 31. 31 different cases. All right. So let's look at in each slot the number comparisons we need. The first slot, this one, we need 1 comparison. Why? Because when you compare with the last one, it is greater than the last one. Then you stop. You can do the insertion. Yep. All right. The second slot, how many comparisons you need? 1, 2. Then you stop. So 2 comparisons. Okay. The next one, 3 comparisons, and so on. Okay. All right. Yeah. How many comparisons do you need here? Compare here with that, right? So all right. So here, to determine, because here how many comparisons we get lost, we cannot keep track of it, right? To figure out that, we use invariant idea. Invariant idea. 1 plus 30, that invariant is 31. 31 is the invariant. 2 plus 29, 31. 3 plus 28, 31. So 31 is the invariant. Okay? Yeah. All right. 3, what number plus 3 equals 31? 28. Yeah. So because when you get into this slot, you need 28 comparisons. When you get this slot, 29 comparisons. All right? When you get to this slot, 30 comparisons. The last slot, because you don't need to do another comparison, the last slot also 30 comparisons. So that's why you add all these numbers from 1 through 30 and another 30. The last one also 30. So that's why another 30. Okay? Yeah. Then, adding up all these 31 numbers, then divided by 31, total number of cases. That is the average number. Here, you do the same thing for 25. 25, we only change that number. Okay? Yeah. Can you solve it by analogy? Yeah. Analogy. That's simple. Analogy. Okay? All right. The last question for this video. Yeah. Question number 4. Yeah. So this time, similar question. Okay? Still insertion, ordered array, right? Insert ordered array. But I added conditions. Greater than the 3rd element and less than 28th element. You need to factor in this factor, then using the similar method in the previous question. Yeah. All right, so here 35 total number. Yeah. Still 1, 2, 3, 4. Okay, all right. So last one, 35, 34, 33. Okay, yeah. 32, too many, 31, 30, 29, 28. All right. Yeah. So smaller than 28. Yeah. So that means you do not consider this part. So not here. Okay, not here. Yeah. Greater than third element. Okay, all right. Greater than, strictly greater than. So not here. Okay. Then only slots. So what are those slots you need to consider? Here. Okay. This part. Okay. How many cases do you have this part? For each slot, the number of comparisons. Okay, using invariant. How do you know the number of comparisons? Using the invariant idea. In the previous question, so you can figure out the number of comparisons in each slot. Okay. Yeah. Finally, the total number of cases. Division. Adding up. Total number of comparisons. Do division on that, the number of cases. That's all you need for this question number 4. All right, so we finish this video D.4.